Now we move to the next logical step in our discussion of the eigenvalue problem for a linear Hermitian operator. In the previous slides, we established the meaning of the eigenvalue equation in quantum mechanics. We saw that if a state is a determinant state of an observable, then its wave function must satisfy the eigenvalue equation of the corresponding operator. Conversely, if the wave function is an eigenfunction of that operator, then the observable has a definite value in that state. So the next question is, what special mathematical properties do Hermitian operators have, and why are those properties so important in quantum mechanics? There are three major results that we will emphasize here. First, the eigenvalues of a Hermitian operator are real. This is essential because a measured value of a physical observable must be a real number, not a complex one. Second, eigenfunctions corresponding to distinct eigenvalues are orthogonal. This gives us a very powerful structural property of quantum states. And third, the eigenfunctions of a Hermitian operator form a complete set, which means we can use them as a basis to expand general quantum states. So the logic here is very clean. Hermissivity is not merely a convenient mathematical assumption. It is precisely the property that makes the operator suitable for representing a physical observable. Real eigenvalues ensure physically meaningful measurement values. Orthogonality allows different determinant states to be cleanly distinguished from one another. Completeness allows us to express an arbitrary quantum state in terms of those determinant states. Each of them has direct physical meaning in quantum mechanics. Let's now prove the first theorem. The eigenvalues of a Hermitian operator are real. Suppose A hat is a Hermitian operator and phi is one of its eigenfunctions with the corresponding eigenvalue lambda. Then we take the inner product of phi with the operator A hat acting on phi, which can be written as shown here. Using the eigenvalue equation, we know that A hat acting on phi must be equal to lambda times phi. We end up with the expression shown here. Now let's look at the same quantity from the other side. Because A hat is Hermitian, we have the hermissivity relation shown here, which is the inner product of phi with A hat acting on phi must be equal to the inner product of the operator A hat acting on phi with the wave function phi. Again, using the inner product and the eigenvalue relations, we obtain the expression shown here. Since the last two equations, they are identical, we must have lambda equals lambda conjugate for any non-zero state or non-zero wave function phi. This means that lambda equals lambda conjugate is only true if lambda is real. This is a fundamental result. It tells us that if an observable is represented by a Hermitian operator, then every possible definite measurement value of that observable is guaranteed to be real. That is exactly what we need physically because experimental measurements do not produce complex values as direct observable outputs. So whenever you hear that observables correspond to Hermitian operators, one of the first reasons is this theorem. Hermitian operators have real eigenvalues. Now we turn to the second important theorem. Eigenfunctions of the same Hermitian operator corresponding to distinct eigenvalues are orthogonal. Suppose A hat is Hermitian operator, and suppose phi 1 and phi 2 are eigenfunctions of the operator A hat with eigenvalues lambda 1 and lambda 2 respectively. Then the inner product of phi 1 and phi 2 must be 0, provided lambda 1 is not equal to lambda 2. To see this, we use the hermissivity of the operator A hat, which is written as shown. We see that the operator A hat can be moved from one side of the inner product to the other side. The result would be exactly the same. So using this expression, the hermissivity of the operator A hat, we have the expression shown here. Using the eigenvalue equations, where A hat acting on phi 2 must be equal to lambda 2 times phi 2, and the operator A hat acting on phi 1 must be equal to lambda 1 times phi 1, we obtain the expression shown here, where we have taken lambda 2 and the complex conjugate of lambda 1 outside the inner product. Rearranging terms, we obtain the final result shown here. The corresponding integral form is given right here. If the eigenvalues are distinct, meaning lambda 1 is not equal to lambda 2, then the factor lambda 2 minus lambda 1 is not 0. Therefore, the only way the equation can hold is that the inner product of phi 1 with phi 2 must be 0. And that is precisely the definition of orthogonality. So the conclusion is, if two eigenfunctions belong to the same Hermitian operator but correspond to different eigenvalues, then they are orthogonal. This result is tremendously important in quantum mechanics. It means that states with different definite values of the same observable are mutually orthogonal in Hilbert space. In other words, they are mathematically independent and physically distinguishable. As mentioned on the previous page, if the eigenvalues are different, then the only way that the last equation shown on the previous page can be true is that the inner product of phi 1 with phi 2 must be 0. Therefore, the eigenfunctions of the same Hermitian operator that correspond to unequal eigenvalues are orthogonal. Okay, so at this point, I would like to emphasize the physical interpretation once more. If an observable is represented by a Hermitian operator, then different eigenvalues correspond to different definite measurement outcomes. The orthogonality theorem tells us that the corresponding eigenstates are orthogonal vectors in Hilbert space. This is one of the reasons Hilbert space geometry is so useful in quantum mechanics. Physically distinct determinant states appear as orthogonal directions in the state space. Now there's one subtle but important point that we need to cover here. This theorem applies to eigenfunctions corresponding to distinct eigenvalues. If two eigenfunctions share the same eigenvalue, they are not inherently orthogonal. In fact, if two eigenfunctions correspond to the same eigenvalue, that is called degeneracy. In that case, orthogonality is not automatic, not inherently true. However, within a degenerate subspace, we can always construct an orthogonal set of eigenfunctions by taking suitable linear combinations. So orthogonality can always be arranged, even if it is not automatic from the theorem alone. And finally, this orthogonality result prepares us for the next major topic, namely completeness. Once we have a set of orthogonal eigenfunctions, we can use them as basis functions to expand more general states. That is what makes the eigenvalue problem so central to quantum mechanics.